Hey guys, this is Professor Janacek. Want to go over convergence tests, some more examples of using the ratio test. So let's try the sum as k goes from 1 to infinity of k raised to the k over k factorial. All right, to begin with, remember we're not going to look at that series. Instead, we're going to take a look at the limit as k goes to infinity of the absolute value of the ratio of the k plus 1 term over the k term. Remember what that means is every time I see a k, I'm going to replace it with k plus 1 in the numerator. So k plus 1 raised to the k plus 1 over k plus 1 factorial. And then in the denominator, I just have k to the k over k factorial. Right, so let's see if we can make some sense of this. First thing I'll do is just clear that complex fraction. Still have k plus 1 raised to the k plus 1 in the numerator and k plus 1 factorial in the denominator. But now I'm going to multiply by the reciprocal. I've got k factorial over k to the k. Oh, let's see, what else can we do? I'm going to do a couple of things here. I recognize that I have a k plus 1 as an exponent. I'm going to go ahead and kind of write that as two terms using some exponent rules. I'm also going to write out the first term of the k plus 1 factorial term. So we have k plus 1 to the k times k plus 1 to the 1 if you need, but you don't need to write that. You don't have to have that 1 there. We still have k factorial there in the numerator. In the denominator, k plus 1 factorial, remember that's k plus 1 times k factorial. And then we still have the k to the k term there in the back. Whew, there was a lot going on there. Hope all of that made sense. Please take your time and make sure that is all clear to you. Now, there you can see a number of things that will cancel. K plus 1 will reduce. K factorial over k factorial, that will reduce. So we end up with the limit as k goes to infinity of the absolute value of k plus 1 raised to the k over k raised to the k, which actually is the limit as k goes to infinity of k plus 1 over k to the k. Let's see, what can we do with this? Well, I will go ahead and take that exponent out of the absolute value. No need for it in there. But now, how in the world do I deal with a variable in my exponent? Now remember, we're going to use a technique, kind of an algebraic technique where I'm looking at inverse functions, specifically the e function and the natural log function. I can write this as the limit as k goes to infinity of e raised to the natural log of k plus 1 over k to the k. Notice again, the argument on the natural log is the argument of that limit. What good does that do? Well, k on the exponent of a logarithm can be moved to the coefficient position. So that gives me the limit as k goes to infinity of e to the k times the natural log of the absolute value k plus 1 over k. All right. Now what can we do with this? Well, let me go ahead, again using some properties of limits and properties of the exponential function. Let me go ahead and move that limit notation up into the exponent. Make sure this makes sense to you. You might not have done this a lot, so please make sure you understand why this is true. All right, so what can I do with this? Well, I'm going to do something that might initially seem a little odd, but it'll make sense here in a bit, I hope. So I have this k as a coefficient. What I'm going to do is write that in the denominator. So I'm going to take this as the natural log of the absolute value of k plus 1 over k over 1 over k. Make sure you recognize what happened here. If I were to clear that complex fraction, multiply by the reciprocal of 1 over k, that would give me a k in the coefficient. I'm going the other way with this. In algebra, we rarely went backwards this way, but here in calculus, we can do all kinds of fun stuff like that. I also want to go ahead and kind of clean things up or make it a little easier to work with up there in the argument of that natural log. So let's write this as 1 plus 1 over k. Again, just looking at this, k over k is 1, 1 over k, of course, is 1 over k. And then we still have that 1 over k there in the denominator. All right, so now what we want to do is figure out how to work with this. I think I'm going to go ahead and use L'Hopital's rule again. The derivative of the natural log. Oh goodness, how do we do that? The derivative of the natural log is 1 over whatever that argument is times, then of course chain rule says I now need to take the derivative of that integrand on itself. So that's the derivative of the natural log, 1 over whatever my argument is. Now take the derivative of that argument. The derivative of 1 plus 1 over k actually ends up being negative 1 over k squared. Take your time with that one. Now in the denominator, the derivative of 1 over k is negative 1 over k squared again. And maybe I should clean this up just so you can see this all is in the exponent. Oh my goodness. Yep, all in the exponent of e. But I now, so again, take your time. Make sure this makes sense. Please pause this. Make sure you can make sense of this. All I did was use L'Hopital's rule. I took the derivative of the numerator and the derivative of the denominator. Right? The derivative of the numerator is right here. The derivative of the denominator is right there. Okay. So now I can simplify this a bit. The negative 1 over k squared, both in the numerator and the denominator, those reduce. So now I just have the limit of 1 over 1 plus 1 over k. And that limit I can take. Notice as k goes to infinity, 1 over k goes to 0. So we have e to the 1 over 1 plus 0. Well, that's just e to the 1, which is e, which is a number. And hopefully you have an idea of what that number is. It's a great number. I know most of you know pi. You should also know e. It's a great number. But I do know that this number is greater than 1. So according to my rules, if that limit is greater than 1, then this series diverges. Well, wasn't that fun? Let's try another one. Let's take the sum as k goes from 1 to infinity of k plus 2 over 2k plus 7. All right, no factorials, no k's in the exponent. This one might be a little bit easier to work with. We'll see. Okay, we are going to take the limit as k goes to infinity of the absolute value of my ratio. So the ratio, remember in the numerator, I just add 1 to all of those k's. So replace k with k plus 1. In the denominator, I leave it as it was. Oh, let's see now. Let's go ahead and combine some things, get rid of that complex fraction. We have k plus 3 over 2k, distribute the 2, add the 7, 2k plus 9. Clear that complex fraction. It gives us 2k plus 7 times k plus 2, or over k plus 2. All right, let's see. I think we can do some multiplication. Take your time. Multiply this stuff out in the numerator and in the denominator. Whatever technique you're going to use, that's fine. Just make sure you know how to multiply all that. All right. Once you do, you should have 2k squared. Let me think. Plus 13k plus 21 over 2k squared plus 13k plus 18. All right. A rational expression, polynomial over polynomial. Not going to use L'Hopital here. Instead, let's go to our handy dandy little 1 over k squared, 1 over k to the power that's highest in the denominator. That's a nice little technique. Okay, distribute that out. We now have the limit. Still need to write that limit notation of 2 plus 13 over k plus 21 over k squared over 2 plus 13 over k plus 18 over k squared. All right, we can take the limit of this. As k gets really large, 3 over k goes to 0, 21 over k squared goes to 0, 13 over k goes to 0, 18 over k squared also goes to 0. Lots of zeros in there. So we end up with 2 plus 0 plus 0 over 2 plus 0 plus 0, which is just 1. Oh, which I was really liking for a bit, but no. If it's equal to 1, this test is inconclusive. So this test did me no good. However, However, there are other tests.